Welcome back to the Deep Dive. Today we're diving into a question that I find, well, utterly compelling. Can artificial intelligence truly think like us?
Hmm.
It's pretty astounding, seeing these large language models, LLMs, writing stories, answering really complex questions, even cracking jokes, and the grammar is often flawless.
It really is. But when you kind of pull back the curtain, how do their cognitive processes, their actual thinking mechanisms, how do they really stack up against, well, the human mind?
That's the big one, isn't it?
It really is. It's fundamental, I think, to understanding what these incredibly powerful AI systems are and, maybe more importantly, what they are not.
Right.
So our mission in this deep dive is really to unpack exactly that. We've looked at a whole lot of sources that give a detailed comparison between AI and human thinking across several really critical areas.
Okay.
Our goal is to cut through those surface similarities, expose the fascinating nuances, and give you a real shortcut to understanding the core mechanics at play here.
Yeah, because the sources we found offer a really illuminating comparison.
Yeah.
They break down how our brains and these LLMs actually handle information. It's not just about the output, which is impressive,
No, absolutely impressive.
but it's about the vastly different paths they take to get there.
Exactly. And to give you that kind of comprehensive understanding, we're going to explore 6 key areas. These really highlight the differences and maybe some surprising common ground, too.
Okay, what are they?
We'll get into how both humans and AI models approach learning, how they process information, the nature of their memory systems, how they engage in what we call reasoning,
Uh-huh.
the unique ways they make errors, and then finally, this often overlooked but really crucial concept of embodiment.
Embodiment, interesting. Okay.
So with that kind of roadmap in mind, let's just jump straight into the first point. Learning.
Okay, learning. Let's unpack this. I mean, both humans and LLMs definitely learn, no question. But the underlying ways they do it seem profoundly different.
Oh, completely different.
When we talk about human learning, it's all about something truly remarkable called neuroplasticity.
Yeah.
Like the brain's incredible ability to literally reorganize its own wiring, its neural networks, just based on our experiences.
Exactly. Just think about it, right? When you learn a new skill, maybe a language or even just a new fact, the networks of neurons in your brain, they aren't static.
No.
They actively adjust. How they fire changes, the synaptic weights, that's basically the strength of the connections between them, they all modify based on how often and how strongly those neurons fire together.
It's that old saying, isn't it? Hebbian theory. Neurons that fire together wire together.
That's the one. It's the very essence of it.
And what's truly amazing about our human learning then is just how incredibly efficient it is.
Yeah.
I mean, how do we manage that? Picking things up from just a few examples, almost effortlessly.
Yeah.
Like, I can hear a new word maybe once or twice, and boom, suddenly I can use it. Or, a single emotional experience can create this lasting memory maybe for your whole life.
It's incredible. And we're constantly learning, too. Updating, adjusting. We're so dynamic.
Which is such a stark contrast to how LLMs learn. Their process uses something called backpropagation. Could you break that down a bit?
Sure. Backpropagation, it's an entirely artificial training process. An LLM processes millions, maybe even billions of text examples, just vast amounts of data.
Okay.
And its internal weights, think of them as millions or billions of numerical knobs. They get adjusted over and over again. The goal is just to minimize the difference between the next word it predicts and the actual next word in its training data.
So it's all about prediction error.
Exactly, reducing that error. And this demands huge numbers of examples and countless passes through the data, forward and backward, refining those predictions.
Right. So while we might hear a word twice, and it's ours, an LLM might need to see that same word tens of thousands of times in training before it can use it reliably.
Easily. Tens of thousands, maybe more. And here's a really critical point. Once that AI model is trained, its parameters, those weights, they're generally static, they're fixed.
They don't change with use.
Not in the same way our brains do. The model's weights don't dynamically update in real time based on a conversation you're having with it. It means an LLM doesn't genuinely learn from interaction in the way a human does, constantly reshaping its internal knowledge.
So it's more like a highly refined but fixed knowledge base. It just refers back to its training.
Pretty much, yes. And that fundamental difference in how learning happens, well, it really sets the stage for how information gets processed next. It's like a domino effect.
Absolutely. That makes perfect sense. How you learn impacts how you process. So, okay, what are the key differences there? Human versus AI information processing.
Well, in the human brain, processing is It's massively parallel and distributed. You've got
Yeah.
billions of neurons, trillions of synapses, all potentially active at the same time. And it's highly specialized. Different brain regions handle different jobs, right? Your visual cortex processes sight, other areas do language, motor control, and so on.
Uh-huh.
But crucially, we process concepts. We grasp these chunks of meaning, and we instantly link them to our prior knowledge, the context, even our emotions. We don't just decode word by word mechanically.
Right. I heard the brain described as content addressable.
Mm-hmm.
Like the meaning itself triggers related memories or ideas.
Exactly. It's less about a specific file location and more about finding related stuff based on the content, the meaning.
Okay, so that's us. How about LLMs then?
LLMs operate very differently. They work with these discrete symbols called tokens. A token could be a whole word or part of a word or even just punctuation.
Right.
So when you give an LLM input, like a prompt, it first encodes that text into a series of numbers vector representations. These numbers then pass through multiple layers in the model.
And inside those layers.
Inside, the model calculates something called attention scores. This is a key mechanism.
Attention scores, what are they actually doing?
Well, they basically determine how much weight or focus the model gives to different parts of the input when it's trying to generate the output, the response.
Okay.
So it's how the model figures out which other tokens, which other words or parts of words are most relevant for predicting the next token in the sequence.
Ah, so if I ask about, say, dogs, the attention helps it focus on dogs and related words it saw during training.
Precisely. It helps it zero in on the relevant statistical relationships in its data, but notice it's still operating at the level of tokens and statistics. It's not working with the concept of dog like we do, furry, four legs, tail wags, maybe linked to your dog.
Right, so LLMs are doing this incredibly complex statistical dance with tokens, predicting the next most plausible one. While we humans are operating on ideas, we build mental models, we understand meaning.
Exactly. The LLM's operation is often described as next step pattern completion. It's just predicting what token comes next, based purely on the patterns learned from all that training data. It's not genuine comprehension.
No underlying understanding of the ideas themselves.
Not in the human sense, no. And that fundamental difference in processing, well, it leads us straight into our next area, memory.
Yeah, memory, another huge piece of the puzzle. And for humans, it's, again, incredibly complex. We have these multi-layered systems.
We really do.
There's sensory memory first, right?
Mm-hmm.
Holding info from our senses
Mm-hmm.
for just a few seconds, like that after image from a camera flash.
Yep, very fleeting.
Then there's working memory. That's like our mental scratch pad. Short-term, limited capacity holds maybe, 7 things for a few seconds?
Around that, yeah. The classic 7 plus or minus 2 items. It's what you use to hold a phone number in your head just long enough to dial it.
Right. And then the big one,
Mm.
long-term memory.
Yeah.
Much larger capacity, maybe limitless, retaining stuff for years, decades even.
Absolutely. And crucially, human memory is deeply associative. Memories aren't just filed neatly away in isolation.
No, they're all tangled up.
Exactly. They're linked by meaning, by context, by emotion. You mentioned the smell of glass cleaner reminding you of a video studio.
Oh yeah, instantly takes me back.
That's association. My brain does it with certain songs and, say, the smell of pine trees from a childhood camp. They're intrinsically linked because they happen together powerfully.
It's like a personal time machine, triggered by a scent or a sound. So amazing.
It really is. Now,
Yeah.
LLMs, by contrast, their memory architecture is much, much simpler, though it holds a vast amount of information.
Okay, how does it work?
Well, their knowledge, everything they learned during training, it's basically encoded as numerical values within the model's weights. That's their version of long-term storage, but it's static, remember.
Right, fixed after training. What about working memory? Do they have an equivalent?
Sort of. The closest equivalent is what's called the model context window. This is the sequence of tokens the model is actively considering at that moment.
So that includes my prompt.
Your prompt, yes. Any prior turns in the conversation, maybe documents you've attached. Basically, the recent input.
Okay, but here's the catch, right? The limitation.
Exactly. Once that context window fills up, and they have limits, sometimes quite long now, but still limited, older information just falls out. It's completely forgotten by the model.
Gone. Not stored anywhere persistently, like our long-term memories.
Correct. So an LLM doesn't really have a long-term memory in the human sense beyond its initial static training. It forgets the specifics of your conversation once they scroll out of the window.
Which really limits things, doesn't it? Like building a relationship or the AI remembering my preferences over time. It has to be constantly reminded by putting things back in the context window.
Precisely. It hinders sustained adaptive interaction in a fundamental way.
Okay, so learning, processing, memory, all quite different. Given these foundational differences, it really makes you wonder about reasoning, doesn't it?
It absolutely does, because we humans, we have these whole cognitive models just for reasoning.
Right, like Kahneman's System 1 and System 2 thinking.
Hmm.
System 1 is that fast, intuitive, gut-feeling judgment.
Quick pattern matching.
And System 2 is the slow, deliberate, logical reasoning, the hard thinking. And we consciously perform that reasoning. We can work through a problem step by step.
We can. Now, what's fascinating with LLMs is that they've mostly been trained on the outputs of human System 2 thinking.
So things like scientific papers, legal arguments, solved math problems, that kind of structured, explicit information.
Exactly. That's the bulk of the high-quality text they learn from. And while researchers have developed techniques like reinforcement learning or chain of thought prompting to coax models into showing intermediate reasoning steps.
Yeah, you see that sometimes where it thinks step by step.
Right, but here's the crucial distinction. The LLM isn't consciously performing reasoning like we do. It's generating a statistically plausible sequence of tokens that just looks like reasoning because it saw similar sequences in its training data.
So it's mimicking the form of reasoning without the underlying conscious process or understanding.
That's the current dominant understanding, yes. When an LLM gets a complex answer right, it's typically because the sequence of tokens it generated happened to align with logical rules it learned implicitly from the data, not because it inherently understands those rules.
Which explains those weird failures, right? Like, wasn't there that famous example of models struggling to count the letter R in the word strawberry?
Yes, that stumped many powerful models for a surprisingly long time. It seems trivial to us, but it highlights that lack of inherent, grounded conceptual understanding. The reasoning is often a very sophisticated mimicry, not true deduction.
Wow. Okay, that naturally brings us to the topic of errors.
Yeah.
Because LLMs definitely make them. One big one is hallucination.
Right. Hallucination in AI means producing these confident-sounding statements that are just factually wrong, made up.
Yeah, confidently incorrect. Now, you mentioned this isn't quite the same as human hallucination, like seeing things.
Generally, no. That's usually linked to specific neurological or psychological states, but there is a human phenomenon in psychology that's actually a much closer parallel. It's called confabulation.
Confabulation. Okay, I've heard that term. What exactly does it mean for humans?
Confabulation is when a person unknowingly creates a false memory, or maybe a false explanation for something they did or something that happened. The key word is unknowingly.
So it's not lying. They believe it.
Exactly. It's not deliberate deception. The person genuinely believes the false information is true. They might vividly recall details of a childhood event that never actually occurred, or offer a perfectly logical sounding but completely inaccurate reason for why they behaved a certain way, and they're totally convinced.
So why does this happen? Is it like the brain just filling in gaps?
That's precisely the idea. The brain has this natural tendency, almost a compulsion, to create a coherent narrative, to make sense of things. When there are gaps in memory or understanding, it sort of papers over the cracks, fills in the missing details to make the story work.
Like smoothing things over.
Right. Daniel Gilbert actually calls it the filling in trick. And it happens way more often in everyday life than people realize, not just in clinical cases. So it's a provocative thought, maybe? Next time you hear about an LLM hallucinating, maybe just pause and consider how often we humans might confabulate in a single day, just our brains trying to create that seamless story from, well, fragmented experience.
That is a thought-provoking parallel. Gives you a bit more empathy for the AI, maybe? Or just makes you question your own recall. Okay, final area. Embodiment. This feels really fundamental.
I think it is arguably the most fundamental difference. Embodiment simply means existing in the real physical world.
Right. Having a body, interacting with stuff.
Exactly. Our thoughts, our understanding, our behaviors are all profoundly shaped by our physical interactions with our environment. Your concept of wetness, for instance. It's not just a definition you read.
No, it's the feeling of water, how it drips, how it makes things slippery.
Precisely. It's tied to tactile sensation. You understand gravity not just from physics class, but because you live with it. every step, every time you drop your keys. Our common sense is deeply anchored in this physical reality.
But LLMs, they're the opposite. They're disembodied software.
Completely disembodied. They exist as code and data on servers somewhere. They don't have bodies. They don't exist in the world.
No tasting, smelling, feeling gravity.
None of it. An LLM doesn't feel the warmth of the sun or the sting of cold. Its knowledge of the physical world is entirely secondhand. It's learned purely from words written by embodied humans who did have those experiences.
It's like learning about swimming only by reading books about it, but never actually jumping in the pool.
That's a great analogy, and that's a huge reason why LLMs often lack basic common sense in ways that seem baffling to us.
How so?
Well, you inherently know that if you let go of a pen, it falls down. Gravity. An LLM might know that too if it read it enough times.
Yeah.
But if its training data, say, accidentally included a lot of science fiction where things float around, without enough grounding in real-world physics descriptions, it could plausibly generate a scenario where you throw a pen and it just floats away. It lacks that anchor in physical reality.
It doesn't have the built-in laws of physics that come from just existing physically.
Exactly. This impacts its ability to understand and predict the mundane, unspoken rules of the everyday world.
Okay, so let's try and bring all this together. We've covered learning, processing, memory, reasoning, error, embodiment. What's the big takeaway?
Well, I think it's abundantly clear that while the outputs can look surprisingly similar sometimes, essays, answers, stories, the underlying nature of cognition in humans and AI is fundamentally, profoundly different.
Right, different paths to get there.
Very different paths. But what's also fascinating is that both systems do learn.
Yeah.
Both process information by adjusting connections in complex networks, both generalize patterns, both predict information.
But they do it through vastly distinct mechanisms.
Incredibly distinct ways, yeah.
Yeah.
Each with its own unique strengths and, frankly, limitations.
So humans bring what? Meaning genuine comprehension.
I think so. We understand not just what something is, but why it matters, its relevance, its connection to everything else. We grasp context and nuance intuitively.
And AI brings speed,
Mm.
breadth of knowledge.
Unparalleled speed and breadth, absolutely. An LLM can synthesize information on a scale a human couldn't even dream of, making connections across vast data sets that would take us lifetimes to read.
So it really points towards combining them, doesn't it?
It really does. The real power seems to lie not in replacing one with the other, but in combining these different ways of thinking.
Like that doctor example.
Yeah.
Using AI to scan all the latest research instantly.
Right. Synthesize research, spot patterns maybe humans would miss.
But then the human doctor uses their own experience, their intuition, their embodied understanding of the actual patient sitting in front of them.
Exactly. Their empathy, their common sense grounded in reality, to apply that AI-generated knowledge wisely to that specific, unique person.
Leveraging the best of both worlds. Human intuition and comprehension, plus AI speed and scale. That feels like where the real potential is.
I completely agree. That combination could unlock entirely new possibilities, achieving results superior to what either could do alone.
So maybe final thought for everyone listening. As we continue to build and integrate AI more deeply into our lives, what new forms of intelligence, or maybe just understanding, might emerge when we truly leverage the strengths of both human and artificial thinking, while really acknowledging their fundamental differences?
That's a great question to ponder.
And maybe reflect on how your own unique experiences, your own embodiment in the world, shapes your understanding. How does your physical interaction with reality influence how you think? What stood out most to you from this deep dive? We'd genuinely love to hear your thoughts and maybe even your suggestions for future topics.
Yeah, definitely.
Thanks for joining us on this deep dive.